Hi, this is Professor Sartor, and I'm back with another 10 problems for my college algebra class. This question says, solve the exponential equation. So we know this is an exponential equation because we have variables in the exponent. I've got a table down here which has the different methods for solving exponential equations. We have relating the bases, which requires us to make both sides have the same base. We're not going to be able to do that with this example because the base on the left is 1.41, which is a decimal with 2 places, and the base on the right is square root of 2. Square root of 2 has infinite decimal places. So we're not going to be able to make the bases the same. So we have these other two methods, converting the exponential to a logarithmic equation, or taking the log of both sides. I prefer taking the log of both sides, so we're going to use that method. So our equation, 1.41 to the x equals square root 2 to the 1 minus 3x. I'm going to take the log of both sides. You can use any base, but I prefer to use natural log. So I'm taking the natural log of each side. Now, because we've introduced the log, we are now able to use all the properties of logs. And the one that we're going to use is called the power rule. So if you have a power on the inside of the log, you're going to be able to pull that power in front of the log or multiply by that power. So I was able to get that variable out of the exponent with the power rule for logarithms. I'm going to do the same thing with the power on the right. Get 1 minus 3x times natural log square root 2. So now on the right-hand side, I'm going to use a distributive property and distribute that natural log square root of 2 to each term inside the parentheses. That would give me natural log square root of 2, because 1 times natural log square root of 2 will be natural log square root of 2. And then minus 3x times natural log square root of 2. On the right, I'm just carrying that down. On the next step, I notice that I've got a variable of x on the left, and I also have a variable x on the right. I want those x's on the same side, so I'm going to add 3x to both sides. Not just 3x, that whole term. 3x natural log square root of 2 plus 3x natural log square root of 2. Now these are not like terms, so I'm just going to write it out. X natural log of 1.41 plus 3x natural log square root of 2. On the right, those two will cancel each other out, and I only have natural log square root of 2. So once I have all those x's on the same side, I can factor out that x. It gives me natural log 1.41 plus 3 natural log square root of 2 equals natural log square root of 2. Now that I have an x by itself here, I'm going to get rid of this parentheses by dividing by natural log 1.41 plus 3 natural log square root of 2. I'm going to do the same thing on the other side of the equation to make sure I balance. So that's going to cancel out this whole parenthesis, leaving me with x by itself on the left. On the right, I have natural log square root of 2 over natural log 1.41 plus 3 natural log square root of 2. I'll put that in my calculator so I can round to 4 decimal places. Natural log square root of 2 over I need parentheses for my whole denominator, natural log 1.41, close parentheses for that natural log, plus 3 natural log square root 2, oops, let me back up there and delete a few things. Okay, there we go. Natural log square root of 2, close parenthesis for the log, close parenthesis for the whole denominator. And to round that to 4 decimal places would be 0.2505. This question says solve the exponential equation 165e to the x minus 2 equals 5. And we're solving an exponential equation. We've got these different methods, relating the bases, converting to a logarithm, or taking the log of both sides. But I wanted to stop for a second and look at these methods and show you that in order to do these methods, you have to have the exponential being by itself on one side. On every single one of these, the exponential part, that's the b to the x part, is by itself on one side. So all of these methods require that. In the example that we have, 165 e to the x minus 2 equals 5, the exponential part, which is this part right here, you can see is not by itself. So we have to start off by isolating the exponential. So we're going to divide both sides by 165. That gives me e to the x minus 2 equals 1 over 33. And now my exponential is isolated. So I can't use these other methods of converting, taking the log of both sides, or relating the bases until I have that exponential isolated. Okay, so now that we have it isolated, I'm going to use the take the log of both sides method. I'm going to take the natural log on the left and take the natural log on the right. I'm able to use the power rule to bring that power out front. X minus 2, natural log e, is natural log of 1 over 13. Natural log of e is the same thing as 1. So we have x minus 2 equals natural log of 1 over, and somewhere along the way my 33 changed to a 13. So let me fix that. 1 over 33. 1 over 33. So now I'm going to get x by itself and add 2 to both sides. And that gives me x equals 2 plus natural log of 1 over 33. So let's type that in the calculator. 2 plus natural log, 1 over 33. And that is negative 1.4965 if we round to 4 decimal places. Okay, this question says solve the logarithmic equation. Log of 9 minus 4x equals 2. So we have two methods for solving log equations that we're going to look at. And one of them is to convert to an exponential, and the other one is to use the one-to-one property of logs. So let's look at both of them. So if you have a log equation like this, y equals log base b of x, to convert it to an exponential, you would take the base b, that becomes the base of the exponent. The log always equals the exponent. So whatever the log equals becomes the power. And then what is inside the log is what that exponential expression equals. So we take our log equation, we turn it to an exponential equation, and hopefully are able to solve from there. So the other method, which is the one-to-one property of logarithms, is when you have both sides of your equation. Notice both sides here have log of the same base. And what you can say is that because both sides have log with the same base, what's inside of those logs have to equal each other. So it allows you to take that log equation and simplify it. So our example is given to be log of 9 minus 4x equals 2. And I want to think about which one of these methods makes sense to use. So remember what I said about the property of logarithms requires us to have log with the same base on both sides. And I don't even have a log on one side of my equation here. So I'm going to go with converting to an exponential for this example. So you can think about these two different methods as having log only on one side and having the log on both sides as a way to tell which method to use. So on this one, we're converting to an exponential. So I need to know what the base of this log is. So I don't see any subscript down here, so that means that this is my common log, and that subscript or base is 10. So I have a base of 10. The log always equals the exponent. So 2 is going to go into that power. And then this expression is going to equal what's inside the log. So that 9 minus 4x is what 10 to the second power equals. So I've converted this to an exponential. Let's simplify 10 squared is 100. And then I want to get the x by itself. I'll subtract 9 on both sides. That gives me 91 equals negative 4x. Divide both sides by negative 4. And I have x equals 91, negative 91 over 4. Every log equation you need to check to make sure you're not taking the log of a negative. So I'll substitute that negative 91 over 4. 9 minus 4 times negative 91 over 4. The 4's cancel. And you've got 9 minus a negative 91. That's the same thing as plus. Negative minus a negative is plus, so we've got 9 plus 91. So that's going to be a positive value, and we'll end up keeping that solution. This example says solve the following logarithmic equation. We have log base 5 of x plus 9 minus 3 equals log base 5 of x plus 29. So looking at my methods that I gave you down here, we have convert to an exponential and use the one-to-one property of logarithms. And I told you earlier that we're looking for logs being on one side or logs being on both sides. But this example shows we have to be careful jumping too fast because I do have logs on both sides. However, that minus 3 kind of throws things off. I need to have logs on both sides and only logs on both sides. So this one I am going to rearrange to make it work for the first method. So to do that, I want the logs on one side and everything else on the other side. Okay, so my problem is log base 5 of x plus 9 minus 3 equals negative log base 5 of x plus 29. Okay, I'm going to rearrange by adding the 3 to the other side. So now I have log base 5 of x plus 9. Move this out of the way. Equals negative log base 5 of x plus 29 plus 3. And now I'm going to move this log so that it's on the same side as the other log, plus log base 5 of x plus 29. They cancel out from this side. The only thing left on this side is 3. On the left side, those are not like, so I can't combine them. So I'll just write them down. Log base 5 of x plus 9 plus log base 5 of x plus 29. So now we have logs on one side, just like that method of converting to an exponential. But the problem is that we have to condense into a single log first. We need a single log before we convert. So we're going to condense to a single log using the product rule. I'm condensing to a product because there's a sum of logs with the same base. So I'm going to have x plus 9 times x plus 29. And now that I have a single log, I can convert this to an exponential. The base of the log is the base of the exponential, so 5 is my base. The log always equals the exponent, so that 3 becomes the exponent. And this exponential is going to equal what's inside the log. X plus 9 times x plus 29 is inside that log, so that's what our expression equals. So now we have 5 to the third power equals x plus 9 times x plus 29. 5 to the third power is 125. Want to multiply this out. That's going to give me x squared plus 29x plus 9x. I'm not sure what 9 times 29 is. Let me multiply it in my calculator. That's 261. I'm going to combine like terms. 29 plus 9 would be 38 plus 261. I'm going to move all the terms to the same side. Let me continue up here. So that would give me 0 equals x squared plus 38x, and 261 minus 125 is 136, a positive 136. So let me try to solve this quadratic by factoring. Get x and x. And let's see, what are factors of 136? Okay, 136 is 1 times 136. It's even, so 2 goes into it 68 times. That number's still even, so 4 goes into it 34 times, and that's the one that's going to do it for us. 4 and 34 make 38. So 4 and 34, both of them plus. I'm going to set each factor equal to 0. Subtract 4 on both sides gives me x equals negative 4. Subtract 34 on both sides. I get x equals negative 34. Okay, but with every log equation you need to check. So let's see our original there. Our original had log base 5 of x plus 9 minus 3 equals negative log base 5 of x plus 29. So if I were to put a negative 4 into this expression, I would get negative 4 plus 9, which is positive, so that's good. If I put a negative 4 into this expression, negative 4 plus 29 would give me a positive. That's good. So we're going to be able to keep the negative 4. Okay, but let's try it again with the negative 34. If I put a negative 34 into this expression, I'm going to get a negative number. Log of a negative number is undefined, so we're going to have to throw that solution away. So the only solution is going to be x equals negative 4. This question says, how long in years and months will it take for an investment to double at 15% compounded monthly? Okay, so the part where it says 15% compounded monthly is going to tell me what formula to use. We're going to use our compound interest formula, which is A equals P times 1 plus R over N to the NT. Now it says compounded monthly, which tells me my value of N is 12 for 12 times a year. Monthly is 12 times a year. The 15% is going to tell me what R is. It's 15%. We put that in decimal form, which is 0.15. So we were given numbers to substitute in for R and N. And the question over here says how long, so that's our unknown. Time is something that we're going to figure out in this problem. And you may think we're not given enough information because we also weren't given numbers for A and P. P is your principal or your initial amount of money, and A is your accrued amount of money after that period of time. But even though we weren't given exact numbers for these, we were given some information right here. We're talking about doubling. How long will it take to double what we started with? So we're not given the exact value, but we are given that A is going to end up being double what we started with, twice as much as P. So let's substitute what we know into this formula. We're going to change that A to 2P, leave P alone, substitute in for R to be 0.15, for N to be 12, N is 12, and we don't know T. Okay, so we're going to start solving, and because we have P's on both sides, P's are factors on both sides, we can divide that factor out. So the P cancels from the left and the P cancels from the right. We have 2 equals 1 plus 0.15 over 12 to the 12t. Now this is all numbers inside the parentheses, so we can simplify that. 0.15 divided by 12 plus 1 is going to give me 2 equals 1.0125. So now I have an equation with only one variable, and that variable is in the exponent. So this is an exponential equation. I'm going to solve by taking the log of both sides, taking the natural log on the left and the natural log on the right. Because I have a log, I can use the power rule to bring that power out of the exponent. So I'm using the power rule for logarithms to give me 12t natural log 1.0125. And now I can get t by itself by dividing both sides by 12 natural log 1.0125 0.0125. Do the same thing on the other side. So that cancels this out, cancels the 12 out, and I have t equals natural log 2 over 12 times natural log of 1.0125. Let's put that in the calculator. Natural log 2 over, I need parentheses around my whole denominator, 12 natural log 1.0125, close parentheses for the log, close parentheses for the denominator. And that gives me approximately 4.6498. I'm going to go 2 more decimal places because we want to figure out how many years and months this is. So this digit right here will be the years. We know it's going to be 4 years. And we're going to use the rest of this to figure out how many months. We know there are 12 months in a year. So we want to take this 0.649802, and this is in years. We're going to multiply that by 12 months to turn it into months. So let's subtract the 4 out and multiply this by 12. And that gives me 7.79, and I need to round to the nearest month, so that's going to be 8 months. So it would take 4 years and 8 months to double if my interest rate is 15% compounded monthly. Okay, this question says, during a research experiment, it was found the number of bacteria in a culture grew at a rate proportional to its size. At 7 a.m., there were 4,000 bacteria present. At noon, the number of bacteria grew to 4,600. How many bacteria will be there at midnight? So we're going to use our exponential growth and decay model for this example, which is A equals A naught e to the kt. So let's make sure we know what each one of these things are. A naught is our starting amount, or we mostly say initial amount. K is our growth or decay rate. T is time. And A is going to be our ending amount after whatever period of time we have. So in this example, it says at 7 a.m. we have 4,000 bacteria. Then at noon, we have 4,600, and we want to know how many we have at midnight. So I want to take these times of the day and convert them to a time that we can use in a formula. So we're going to say that 7 a.m. is our beginning time, and then we'll figure out how many hours later that will be at noon. So starting at 7, we have 8, 9, 10, 11, 12. So 12 is noon, so T equals 5. And then midnight is 12 hours later from noon, so 12 plus 5 would be 17 hours. So our ultimate goal is to fill in this missing piece of information, how much bacteria is there at midnight. But in order for us to do that, we need to figure out K, the growth or decay rate. In this case, it's growth. We grew from 4,000 to 4,600. So what we're going to do is we're going to focus on just these pieces of information here so that we can figure out what that growth rate is. So what I'm going to do is I'm going to use the 4,000 as my starting amount, the 4,600 as my ending amount, and t equals 5 as my time, and I should be able to solve for the growth rate. So I have a equals a naught e to the k t. I grew to 4,600. I started at 4,000. I don't know the growth rate, but after 5 hours, I grew from that 4,000 to 4,600. So now I'll be able to solve this exponential equation for k. First, I'm going to isolate that exponential. I isolate it by dividing both sides by 4,000. Okay, I can reduce that a little bit. These zeros cancel out, and I have 46 over 40. See, those are both even, so into 46 would go 23 times. 2 goes into 40 20 times. I have e to the 5k. Then I solve this exponential equation by taking the log of both sides. I can use the power rule to bring that 5k out front. Natural log e is equal to 1. So I have 5k equals natural log 23 over 25. Divide both sides by k, and now I have the growth rate. Natural log of 23 over 25. I apologize. I changed that 20 to a 25 for some reason. Let me put it back to 20. 23 over 20. 23 over 20. All over 5. So that is our growth rate. And now that we know our growth rate, we're going to be able to find that missing value that we talked about up here. We're going to use 4,000 as our starting amount. We're trying to figure out our ending amount. We're going to use time as 17, and we're going to use that growth rate that we just found. So in our formula, A equals A naught e to the kt. We started off with 4,000 bacteria. And k we just found to be natural log of 23 over 20 over 5. And our time is 17 hours. Remember, we started at 7 a.m. That was time equals 0. Midnight will be 17 hours later. And we'll put that in our calculator. So we have 4,000 E. And I like to put the 17 in the front. It's a little bit easier to type in the calculator. So do 17 times the natural log of 23 over 20, close parenthesis for the log. Then I need to divide by 5. So we have 1.1084 times 10 to the 15th. So that means we've got to move that decimal place 15 places to the right. So that's 4 places. That's 15 places. All right, that number looks a little bit big. So I'm looking back over at my calculator here and I see that I'm missing a division sign. So let's fix that. Let me type that in again. 4,000 e to the 17 times the natural log of 23 divided by 20. So now I've got that division sign there, and then divide by 5. That's a little bit more reasonable. That jumped up way too much. Okay, so now we have 6,433 bacteria at midnight. A certain radioactive isotope is a byproduct of some nuclear reactors. Due to an explosion, a nuclear reactor experiences a massive leak of this radioactive isotope. Fortunately, the isotope has a very short half-life of 15 days. Estimate the percentage of the original amount that remains 9 days after the explosion. Okay, so we're going to use our exponential growth and decay model for this, which is A equals A naught e to the kt. So what we need to do is figure out the growth rate based on this piece of information right here. We have a half-life of 15 days. So obviously 15 days is a reference to the time, but this half-life is really important for us to figure out the problem. A half-life of 15 days tells us that we're going to have half of what we started with after 15-day time. So we can make this relationship. We can say that the amount that we end up with is going to be half of the amount we start with. So we know it's going to have this relationship at 15 days. So this is going to allow us to find the growth rate of our radioactive isotope. So we have us ending up with half of what we started with. So I changed A to 1/2 A naught because that's what we have over here. We're going to leave that A naught. We're trying to figure out K, and in for time, we're going to put 15. Okay. So now we're going to be able to solve this exponential equation. We're going to divide both sides by A naught, and it ends up canceling out on the left and canceling out on the right. And we have 1/2 equals e to the 15k. I'll take the natural log of both sides. I can use the power rule to bring that 15k out front. Natural log of e is 1, so this is going to be 15k left on the right. I can divide both sides by 15. So I get k, the decay rate, is natural log 1/2 over 15. So I know my growth rate now. So let's go back to the problem again. The problem says to estimate how much is left 9 days after the explosion. Actually, what percentage of the original amount. So I'm going to go back to my formula again. A equals A naught e to the kt. And we want to know 9 days. So now t is going to equal 9. And I'm also going to, so I'm going to substitute in for T9. I'm also going to substitute what we figured out for K. and then we'll be able to figure out the percentage. So we get e to the natural log 1/2 over 15 times 9. So I'm going to put this in my calculator. E, and I'm going to move this 9 to the front. It's a little bit easier to type. 9 times natural log of 1/2 or 0.5, close parentheses for the log, and I'm going to divide by 15. So that gives me A equals A naught times 0.6597. So I'm going to read this, and this is going to say the amount I end up with is equal to this percentage of what I started with. So this is ending amount, starting amount, and this is going to be the portion that is remaining, portion of that starting amount. So if I round that, that'll be 0.66 or 66% of what I started with is left after 9 days. Solve the system by substitution. System is a group of equations, and we're going to solve them simultaneously. So we're looking for an ordered pair, an x and a y, that makes the first equation true, but also makes the second equation true. We're going to solve by substitution. So solve by substitution, you're going to choose one of the equations, the first one or the second one, and solve for one of the variables, either x or y. So I have a choice here. I can solve for x in the first equation, y in the first equation, x in the second equation, or y in the second equation. You can solve for any of them, and it will work, but I'm trying to avoid as many pitfalls as I can, and pitfall for most students is fractions. So if I choose to solve for this x or this y, you notice they don't have a coefficient on it, and those will allow me to avoid having fractions in my equation. So I'm going to use the first equation, and I'm going to solve for the x. So let's get x by itself. I subtract 2y on both sides. That gives me x equals negative 2y plus 3. Here's where the substitution comes in. This is equal to x, right? So I'm going to put this in for x in the other equation. So that gives me 2 times negative 2y plus 3 minus y equals negative 4. This now gives me an equation with only one variable in it. I can solve it with the distributive property. It's negative 4y plus 6 minus y equals negative 4. I'll combine like terms. That's negative 5y plus 6 equals negative 4. Subtract 6 on both sides. That gives me negative 5y equals negative 10. Divide both sides by negative 5, and y equals a positive 2. So my solution is an ordered pair. I don't have the ordered pair yet. I only have one coordinate of the ordered pair. I need to find the other coordinate. So I'm going to take this y equals 2 and do what's called back substituting. I'm going to substitute this y back in over here. That would give me x equals negative 2 times 2 plus 3. X equals negative 4 plus 3, which is negative 1. So now I have that ordered pair, and this is the solution to the system. Use the method of elimination to solve the system of linear equations. We have 2x minus 3y equals 32. 3x plus 6y equals negative 15. All right, now to solve by elimination, the first thing you want to make sure is that all of your variables are lined up. I have my x's lined up, my y's are lined up, my constants are lined up, but most important of all, the most important thing is to make sure that your equal sign is lined up. So I have everything lined up, and then what we're going to do is we're going to add the equations together. Okay, let's check that. When we add the equations together, what we want to happen is we want a variable to eliminate. So right now, if I added my x's together, would the x's eliminate? No, you would get 5x. If I added my y's together, would the y's eliminate? No, I would get 3y. So right now, it doesn't work, but I'm going to force it to work. So what I want to do is choose which one to eliminate. Choose x or y, it doesn't matter which one. So let's choose x. What I want to do is I want to force it so that when I add those x's together, they're going to cancel each other out. So they need to be the same number with the opposite sign. So I'm going to find the least common multiple of the coefficients of x. That's going to be 6. 2 goes into 6 evenly, 3 goes into 6 evenly. That's our least common multiple. So if I want to change that coefficient, of 2 to a 6, I need to multiply by 3. I'm going to multiply that whole equation by 3. If I want to force this coefficient of 3 to be a 6, I need to multiply that whole equation by 2. Okay? But that's not going to work either, because that would give them both be 6. 6x plus 6x would be 12x. Remember, we want it to eliminate. So we need one of these to be a negative to make that work. That would make one of them a positive 6x, the other one a negative 6x, and when you add them, it'll eliminate. So let's multiply that 3 by every term in the first equation. That becomes 6x minus 9y equals 36 times 6 is 216. Negative 2 times 3x is 6x. Negative 2 times 6y, so negative 12y. This should be negative. Negative 2 times 3 is a negative 6. Okay, and negative 2 times negative 15 will be a positive 30. Now we're going to add the equations together. You see why we want them lined up so that we add the like terms together? So the 6x's cancel. We'll combine the y's together to get a negative 21y. $216 plus 30 would be $246. I'll divide both sides by negative 21, and that gives me, and I'm pausing for a second because I just caught a mistake of mine. If you go back to the original problem, notice this up here says 32, but I wrote 36, so let me fix that. At 32, that should be 32, and 32 times 3 would give me a 96 here. And 96 plus 30 would give me a 126 here. And 126 divided by 21, negative 21 would be negative 6. Okay, so we have the y coordinate. Now we're going to get the x coordinate. So what we do is we take that y equals -6, and you can substitute it in for this y, or you can substitute it in for this y. Either one will work. So we have y equals -6, 2x minus 3 times y equals 32, 2x plus 18 equals 32, subtract 18 on both sides, gives me 14, 2x equals 14, divide by 2 and get x equals 7. So our solution is 7, -6. Okay, use the substitution method or the elimination method to solve the system. We have x minus 3y equals 16, 4x minus 12y equals 16. So let's see. For the substitution method, I think I would solve for this x, so let's try it with the substitution method. We solve for one of the variables. I chose to solve for x because that doesn't have a coefficient. It allows me to avoid fractions. So I added 3y to both sides. That gives me x equals 3y plus 16. Then we're going to substitute this in for the other x. It gives me 4 times 3y plus 16 minus 12y equals 16. I'll start solving this with the distributive property. That's 12y, 16 times 4, 64. I'll combine like terms, 12y minus 12y. The y's cancel each other out, leaving me with just a number on the left and just a number on the right. Now, when all the variables cancel out, what that means is that you have a special case. Special case. In this case, we look at the final statement, and that final statement is clearly something that is false. So if that final statement is false, we know that this system has no solution.